RAID. In this nugget, we'll talk about RAID, which may be what comes to mind first for you as bug spray, but and what we're going to talk about today is a system that you can set up to increase disk performance. For most RAID systems, you need at least 2 hard drives on your system. Now, this is not something that the typical home user would have interest in, although I have seen high-end gaming computers that came with RAID controllers already installed. And many commercial installations can benefit from RAID, especially if there seems to be a disk I/O bottleneck on the system currently. So pull up a chair and let's get to work. Well, let's start this nugget out by talking about RAID. RAID stands for Redundant Array of Inexpensive Disks. So the idea behind RAID is that the disk subsystem is typically the slowest part of our computer. CPUs are fast, transfers to main memory or RAM is very, very fast. But anytime you have to do disk IOs, that slows things down. And if you have a certain application that does lots and lots of disk transfers, whether it's reads or writes or a combination of the two, then that becomes the bottleneck, the disk subsystem. So one solution to having a faster disk subsystem is to buy really expensive, large capacity, high performance disks. Large capacity disks that spin really fast, okay? But it's very expensive to build large capacity disks that spin very fast. And so the idea behind RAID is that we can use these inexpensive disks that, they'll spin very fast, but they won't have nearly the capacity that a very large disk will have. But we'll use a whole array of these or a whole series of these inexpensive disks so that we can have large capacity, we can have high performance, yet our solution will be cheaper than if we just bought the high-end, high capacity, really fast spinning disk drive. Okay? So that's our goal with RAID, is that we want a high performance disk subsystem, but we're going to use these inexpensive disks. And in addition to getting large capacity and high performance from this array of inexpensive disks, depending on which RAID level we use, which we'll talk about in a few minutes, we can also provide data security by using RAID. And what I mean by that is certain parts of your files could get corrupted, and we can recover that data by using RAID. All right, so let's move on and talk about the different RAID levels. So there's 3 main RAID levels that we want to talk about: level 0, level 1, and level 5. All right. Level 0 is also called disk striping. In this RAID level, what you're going to do is break up a file and stripe it, break it into pieces and put a little piece on each disk of the array. Okay, and that just allows you to do faster transfers because you can access many disks at one time. Level 1 is disk mirroring. In this RAID level, what you're going to do is you're going to mirror. Every hard drive is going to have sort of a backup hard drive that's going to be a mirror image of it. Okay, so in this case, you're going to have great data integrity. If any single disk failed, you can just bring a new disk online immediately, and you'll be back in action. And we'll take a look at these in a couple minutes with more pictures. And then level 5 is disk striping with distributed parity. So that's a whole mouthful there to swallow at once. But we'll build up to that by talking first about RAID level 0. Okay, so RAID level 0, what I've said here is that there's a processor out here, and then there's a whole bunch of these inexpensive disks, okay? It can be as few as like 2, that's very typical for small, for small systems. For high performance, like scientific computing systems, this might be in the dozens. Okay, and so the idea here is that all of these disks are out here. In RAID level 0, they're all what we call data disks. So basically what happens is if you have some file, okay, and I'll just represent this file as a big rectangular box. Okay, well, the way that we're going to store this file in a RAID array is we're going to take the first little piece and we're going to write that to the first disk. We're going to take the second little piece and write it here. We're going to take the third little piece and write it here, and so on. And then, we'll come out, maybe this little piece we write here. And then this little piece here, that gets written back to disk 1. Okay, so and then of course this one gets written to disk 2 and so on. You can see. So we basically write the first piece, the second piece, the third piece, da 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 da. The 10th piece, and then the 11th piece comes back here, the 12th piece, the 13th piece, and so on. So this is what we call disk striping, because this file Now, it's spread across all these different disks. So if I want to read this file from the disk subsystem and bring it into main memory, then what I do is I request, the CPU requests that file, and then the RAID subsystem, this disk can spin and pull up, the first piece, the 11th piece, whatever. This one can pull up the second piece and the 12th piece and so on. And while this one is pulling up the first piece and the 11th piece, this one can be simultaneously pulling up the second and the 12th. This one can be pulling up the third and the 13th and so on. And then all those transfers can happen, and then we can reassemble all the data out on the processor and put it into memory. So typically the slow part of disk transfers is actually the part where you're recovering the data from the disk as it's spinning, and by distributing that over a bunch of different disks, then in essence, this is like parallel processing with disks. Okay, is that we're having lots of things work for us simultaneously, and so that becomes less of a bottleneck that way. Now, the danger here is that because these are all data disks, that if any one of these disks went and failed, then every one of our files that is stored on our disk subsystem is now corrupt, because every file was spread across all the different disks, and so by losing one disk, we run into problems. Okay, and that's a big problem, that we then lose all of our data because we lost one disk. So the next step in RAID is RAID level 1, and RAID level 1 allows us to have disk failures and still recover all of the data. So here what I've done is I've drawn like a series of disks down here that are low, and then the ones up here are high. The high ones up here, the ones on top, are what we're going to call the mirror disks. Okay, and the low ones down here are the data disks. Okay, so it works the exact same way as RAID level 0. You can stripe things across, do whatever you want, but this disk and this disk are mirror images of each other at all points in time. So every time I write to this disk, I also write to this disk. Every time I write to this disk, I also write to this disk. So at any one time, if some disk failed, like this one, well, then what I can do is I can just bring this one online, and everything just runs smoothly as it did before, and then I have some time to replace this disk, get it back into functionality, get a new one in there, and then I'm back up with mirroring again. But for the interim, when this disk failed, I can bring this one online, and then this one will be, since it was a mirror image of this, the one that failed, then we're going to have data integrity. We didn't lose any files or any part of any file, even though we just had a disk failure. And in actuality, if this disk failed and this one did and this one did, we have backups for all of them in place immediately. Now, if it was like these two that failed, then we're in a problem there. But basically, what we want to be able to handle is any single one disk failure, and then we've got a backup for that disk. All right, well, now let's talk about RAID level 4. This is not very commonly used, but it's much easier to describe than RAID level 5. And you'll see by describing RAID level 4, the idea for RAID level 5 will just sort of pop into your head as a natural improvement. All right, so now what we've got is we've got a bunch of data disks, and then we've got one disk out here that's the parity disk. So the idea is that, RAID level 1 was nice, like we could handle any disk failure, but to hold, for 5 disks, for 5 data disks, we needed 5 mirror disks, and that, doubled the cost of our system. So RAID level 4 is going to give us the same sort of data recovery ability. Okay, in that if any one of these disks fails, we'll be able to recover all of the data. But the way that it does it, instead of mirroring all of the data, disk for disk, and have a copy of every single disk, it uses what's called a parity disk, and it uses like the most simple sort of error correcting system that is known to computer scientists. So let me explain this on a really simplistic level. Okay, so here's some bits. Okay, let's just write out some data bits that are stored on here. And typically, when you write to disks, you don't write bit by bit. You write in these large blocks, like 512K blocks or something like that. But let's just explain it in a bit by bit fashion. So say I write a file out here, and I write out the file, and it's like 10011. Okay, now because there's an odd number of ones there, I'm going to write a 1 on the parity disk. If there was an even number of ones there, I would write a 0 on the parity disk. Okay. And so, so the first bit of every disk has been written. It's 10011, and then the first bit on the parity disk is a 1. Similarly, if I write, the second bit on every disk, I write 10110, okay? Well, again, there's an odd number of 1, so I'm going to write a parity disk. Okay? A parity bit of 1 on the parity disk. Okay. Similarly, the third bit of each of these disks, let's say it's 00000. Okay, they're all zeros. Then the parity bit is a 0 because there's an even number of ones. There's 0 ones, and that's an even number of ones. Okay, so now what can happen is one of the disks can fail. All right, and let's just pick a disk at random to fail. Let's just say this one failed here. Okay, so we lost all of this data. We lost all of these zeros that were part of some file. Okay, now what we can do is, okay, this disk failed. We can put a new disk online and we can recover this data by just looking at the other disks and the parity disk. So basically what I'm going to do is I'm going to say, okay, I need to put a new disk online for this one. So, okay, I put the new disk online, but then I need to write out all the data that was on that disk. So the way that I do it is I say, okay, there's a 1 there, a 0, a 1, and a 1. Okay, so there's 3 ones that I've seen so far, and the parity says a 1. So that says there's an odd number of ones. So, using a little logic, there's 3 ones that I've seen already, and there's something missing. But there was an odd number of ones before when this disk was up and running, so that bit there had to be a 0. Because if it was a 1, then there would be an even number of ones, and the parity bit would be a 0. So this parity bit allows us to basically infer what bit was written on this disk. Okay, and the same goes for this one. I look here, I go 1, 1, 1. Okay, that's an odd number of ones. Parity bit says there should be an odd number of ones, so I recreate that with a 0. Okay, here it's 0, 0, 0, 0. That's an even number of ones. The parity bit says there should be an even number of ones, so again, that should be a 0. Okay, and that just allows us to recreate all of the data on this disk. Once we rebuild that, then we can bring this disk, back online, and now our whole RAID array is back up and running, and we handled a disk failure, and we didn't lose any data in the process. Now let's just talk a little bit about the performance of RAID level 4. What has to happen in RAID level 4 when there's a read? Well, it's just like RAID level 1. All of the data is spread out across all these different data disks, and we go ahead and this is seeking for the first part of file 1, this is seeking for the second part, the third part, the fourth part, the fifth part. All those seeks are happening simultaneously, so we're speeding up the process, and then those reads can come into the processor, and we can reassemble them in the processor. Okay, now what happens on a data write with RAID level 4? Well, when I go to write data to any, if I change some part of some file, say I'm going to change this bit to a 1, all right, that's part of my write process. Okay, well, when I change this bit to a 1, it used to be a 0, so what do I have to do now? I've got to change my parity bit to a 1 as well to represent now that there is an odd number of 1s in the third position on all the disks out there. Okay, so every time that I do a write to any of the data disks, I also have to perform a write to the parity disk if I actually change the data on the data disks. So if I change it from a 0 to a 1, then I also have to change the parity bit from a 0 to a 1 or from a 1 to a 0, whatever it was. Okay, and so that creates a bottleneck on the parity disk because every disk write, maybe I do a disk write here, and I do a disk write to this disk, and I do a disk write to this disk. Well, for every one of those, I have to also write to the parity disk, so this becomes a bottleneck. So the natural idea then is, the natural extension of this is RAID level 5. All right, well, the idea behind RAID level 5 is that we're going to distribute the parity across the disks. So we don't have that bottleneck like we just saw with RAID level 4. So let's draw out another little picture here. So here we're going to write out the bits on all the disks and just say the very first position on all the disks are bits like this. Okay, so 10100, and now the parity bit for this, for all of this data is 0 because there's an even number of ones. Now also what I'm going to do is I'm going to underline this bit to represent that that's the parity bit for the first position. But in RAID level 4, what we would do is, the second bit of data would have all the data bits would be out on these disks, and then this would be the parity bit on this disk. But instead of doing that and getting that bottleneck, what we're going to do is we're going to put the parity bit for the second bit of data on the second disk from the right. Okay, so now what I'm going to do is I'm going to write out the bits there and say it's 110. Okay, now what's the parity bit for this? Well, there's an odd number of ones, so the parity bit is a 1. But the parity bit lives on this disk for the second position. Okay, where is it going to live for the third bit position? Well, it's going to live on this disk. So if that position is like 10000, then there's an odd number of ones, so the parity bit on that disk is a 1. Where is it going to live for the fourth position? There. Where is it going to live for the fifth one, the sixth one? Where's the seventh one? It's going to come back here, and we're just going to keep cycling through. So we have the exact same thing as RAID level 4 in that we have our data, spread out across all of the disks, and then we're going to be able to recover the data with this parity bit. So if any disk fails, we can still recover everything on that failed disk by looking at all the other positions on the other disks. Okay, so for instance, if this disk failed, okay, well now we go through and we say, okay, well there's a 1, and 2 zeros, and the parity bit is a 0. So that means the missing bit must also be a 0 because this says there's an even number of 1s and I've already seen 2 of the 1s, so I know this must be a 0. So I can recreate that one, check. Okay, then on this one I go through and I say, okay, well I see 2 1s and I see a parity bit is also 1, which means there's an odd number of 1s, and so this one must be a 1, check. Okay, well now this one, the parity bit is what got destroyed, right? And so all I have to do for this one is just go through and say, okay, well there's an odd number of 1s out here, so the parity bit must have been a 1, check. Okay, so I can reconstruct all of this data because when I lost that disk, and yet I'm not seeing the same kind of bottleneck that I saw with RAID level 4 where all the writes had to write to the same disk to fix the parity. It just depends on what bit position you're writing to on the disks as to which disk you have to write to change the parity bit. All right, well, so far we've talked about RAID at a pretty abstract level. We haven't talked about any implementation details with respect to RAID. But basically, there's 2 ways to implement RAID, and that's with hardware or with software. So for hardware RAID, what you have is a controller that handles all the aspects of the particular RAID level that you're implementing. So you've got your processor out here, and then you've got your disks out here, okay? But in between the processor and the disks is a RAID controller. So the processor plugs into that controller, and then the controller plugs into all the disks, and the controller takes care of everything with respect to RAID. So the controller takes care of striping the data. It takes care of mirroring the data if you're doing RAID level 1. It takes care of the parity bits if you're in RAID level 5. Okay, and to the operating system, this controller makes it just look like there's a single disk. Okay, so the hardware RAID makes the RAID array appear as a single disk to the operating system. So everything in the operating system is just like write this file, read this file, that sort of thing. And the controller is taking care of all the performance aspects and all the overhead and the bookkeeping that RAID has to do. Okay, now hardware RAID is somewhat expensive. This controller has a lot of logic built into it. It's got a lot of functionality, so that is a very expensive piece of machinery. Typically with hardware RAID, the disks that are out there are SCSI disks, which are more expensive disks than IDE disks, for instance. Okay, so hardware RAID requires quite a bit of cost, quite a bit of money to get it started, but it's very, very high performance. All right. The alternative to hardware RAID is software RAID. And software RAID, instead of having a controller that takes care of all the disk writes, then it's all implemented in the kernel. So the software, the operating system itself takes care of, taking that file that needs to be written out to disk and saying, okay, this one needs to be written to disk 1, and this little piece needs to be written to disk 2, and this little piece needs to be written to disk 3, and so on. But the advantage of software RAID is that it doesn't require any expensive controllers or a hot swap chassis or anything like that. A hot swap chassis is just something that allows you to unplug a disk from your system and plug a new one in without rebooting your system. Okay, so those are expensive pieces of hardware. Controllers, hot swap chassis, SCSI disks, things like that are all expensive. Software RAID doesn't require any of that stuff. And software RAID, like I just said, can work with IDE drives. It doesn't need to work with SCSI drives. It can work with SCSI drives just as well, but it can also work with the cheaper IDE drives. So software RAID is a cheaper alternative in terms of raw performance. Hardware RAID is always going to be a little bit better than software RAID, but because processors are so fast nowadays, software RAID is not that big of a performance hit. And in terms of performance per dollar spent, software RAID is going to blow away hardware RAID for normal applications. If you're a high performance computing guy at like Sandia National Labs or something, and you're running some crazy simulation on, I don't know what they run at Sandia National Labs, but some cryptography thing or something's going on, then and you just care about performance, you don't care about dollars because it's just taxpayer dollars anyway, right? So then you would probably stick with hardware RAID, because what you really care about is performance. Whereas for normal people, normal installations, software RAID is going to be a better alternative. Well, there's some tools that are available that help you to configure and manage RAID arrays in Linux. On SUSE Linux in YAST, there's actually, if you go to the System tab and then the Partitioner tab, you can get to an Expert Partitioner screen where you can set up RAID arrays. In order to do that, though, you actually have to have some spare disks or some spare partitions on your system, which I don't have, so I can't walk you through that. However, what you need here, on the pictures on our whiteboard really, they inferred that you would dedicate an entire disk to the RAID array. You'd have like multiple disks, and those entire disks would be part of the RAID array. In reality, you only need to have a partition on each of those disks that's dedicated to the RAID array to do software RAID like we're doing here. Okay, so like if I had a partition out there like /dev/HDB1 and /dev/HDB2, or HDC1, sorry. So HDB1 and HDC1. So the first partition on two different disks. Then I could create a RAID array from those two partitions, even if those disks had other stuff on it that was not involved with the RAID array. Okay, so the other thing is those partitions should be of equal size so that RAID functions properly. If they're not of equal size, then things get messed up. Okay, so that's one way to do it, is using the YAST tool to create some partitions and to create a RAID array. A way that's more common and more universal to other distributions of Linux is to use this tool called MD-admin. MD stands for multiple device. So like a RAID device is like a multiple device. It uses the MD module in the Linux kernel to administer this. The old way to administer RAID from the command line was via a piece of software called RAID Tools, but that's pretty much gone now, and it's been completely replaced by MD-admin. So anything you see referencing RAID Tools, forget about it. Just look up MD-admin commands. And MD-admin just has a bunch of options that allows you to do everything with RAID. Everything from creating a RAID device to managing the arrays to monitoring the performance and so on. Okay, so if we go down here, you'll see that it supports RAID level 0, RAID level 1, RAID level 4, RAID level 5, as well as some other things that we didn't talk about, which aren't so important for us right now. And then the other thing is that it breaks it down. The man page is broken down, and the commands are broken down into 7 major modes of operation. The first thing that you have to do if you're going to create a RAID array is use the create options. So basically what you would do is you would say MD-admin, and you would say -C to create, and then you would give a device like /dev/MD0. So you have to give some device that starts with that MD, that multiple device moniker. Okay, so /dev/MD0, and then you would specify some things like -L0 to do RAID level 0, -L5 to do RAID level 5. Then you can say -N2 to specify that there's 2 devices as part of your RAID array. Okay, so you specify the level, you specify the number of devices, and then you actually list out the partitions that are going to be part of the RAID array. So then you would specify like /dev/HDB1 and /dev/HDC1 and so on. Okay, and then once you create the RAID array, then what you need to do is start it or assemble it. So you would use the commands like mdadmin -a for assemble, and then you would say /dev md0, and that would assemble the RAID array and get it online. And then once the RAID array is online, then it gives you all sorts of tools to do things like manage the array. So you can go in and remove hard drives. You can add hard drives. You can grow your RAID system. Maybe you want to add some more disks to your RAID array. Well, you can do that as well with the mdadmin command. Another thing that you can do is follow or monitor the progress of your RAID array. So you can set it up so that if there's any errors, mail can be sent to the system administrator. You can pull it every 5 minutes or something to look for particular issues that are going on, and if there, like I said, if there's anything that's a problem, then you can have something flagged and some email sent, and then you can come as a system administrator and manually manage the array by taking some disk offline and then putting a new disk in place, and then restoring all the data on that disk, like if you're using RAID level 5, and the mdadmin command allows you to do all of that, and all of that is detailed in the man page. And like I said, this is the new way to manage RAID. Don't use the old system, which is RAID tools. All right, well, it's time to wrap up our nugget on RAID. We started by giving an overview of RAID and talking about the different RAID levels. Remember, RAID level 0 was when we distributed data across multiple disks so that we could parallelize disk transfers. So whether they were disk reads or disk writes, we could have lots of operations going on at once and getting pieces, lots of different pieces of the same file transferred at the same time to increase disk performance. But RAID level 0 offered us nothing in terms of data integrity. If one hard drive failed, then all of our files lost some piece of information, and they all became corrupted in some sense. And then RAID level 1 was the mirroring system. So each hard drive had a mirror image. So disk writes took a little bit extra time because they had to really write to 2 different hard drives. The cost of RAID level 1 is kind of excessive because for every drive of data we have to have another hard drive that's just a mirror image that doesn't even get used usually. And then RAID level 5 was this way, sort of an advanced way to get the disk striping so that the files were spread out over lots of disks. And we also had the capability to recover from a single disk failure by using the parity idea that we talked about. Then we compared hardware RAID to software RAID. Basically, hardware RAID required money and disk controllers and things like that, and it made it look like the RAID array was a single disk to the operating system, whereas software RAID was taking care of everything with regards to RAID within the kernel. And then we talked about configuring software RAID on our system using the mdadmin command. And this is the new way to monitor and manage and create RAID arrays on all the different Linux distributions that are out there. Well, I hope you found this nugget informative, and thanks for watching.